Get started. So yeah. Just a reminder after this. We're gonna take a picture, okay? So after that, we're gonna go to lunch. And for the second talk, we have Alvaro, who's gonna tell us about efficient Gibbs samplers.
Yeah, thanks a lot, Isaac, and thanks for inviting me here. And thank you all for listening. Yes, so I'm gonna tell you about some recent progress we've been working on the topic of I guess modeling thermalization with quantum computers. So and some new developments that have been happening in the field of quantum algorithms for this kind of task. And actually, I'm gonna be telling you about the results from 3 different papers. The first 2 are done in collaboration with Gibbs and Daniel, who are both in France, except for that Daniel moved some months ago to Copenhagen. And the last one, which is I'm going to be talking about them in the opposite order, opposite chronological order. It was done in collaboration with Mateo, who's my postdoc in Madrid, and he's been doing quite some great work on the open systems part of his story. I'll be telling you about this. But first, actually, since I come from kind of a bit far away, and maybe not all of you know where I come from, I just wanted to briefly tell you that basically I'm based in Spain, in the capital of Spain, in Madrid, and we have a physics institute in the north of the city, which is mostly well known for string theory, particle physics, and so on. So most of the grad students that come through us still want to work on that. We're trying to convince them not to, but okay. But actually we are a growing group with 5 quantum faculty and a bunch of students and postdocs. So if you're ever in the area, please come and visit. And yeah, maybe you know this, but just for reference, this is the Real Madrid Stadium. So that's where we are compared to it. I think now it's changed actually. This is an old photo. Okay, so I want to start with a very general question. And the question is whether we can use quantum computers to understand quantum many-body physics and quantum many-body systems, right? And I guess you probably all agree that the answer to this question is yes. But and the answer really is the reason why we can say yes is that because we're able to program and probe quantum physics in what are presumably computationally efficient ways within the paradigm of quantum computation, right? But really, in order to be able to answer this question, let's say with good reason, right? We have to fill gaps in a research program, I will say. And I like to divide this research program in 4 different stages, right? The first is that we want to identify interesting physical processes, quantum processes, and then we would have to understand how to model them as physicists. And then once we have a model of that kind of physical process, then we want to know if you can actually solve it, if you can simulate it efficiently with a quantum computer, and then ideally, you will also like to have some sort of complexity theory understanding of, what's the simulation power of being able to do this. Maybe this is a bit abstract, but the example I like to put forward in this case is one that you probably all are very familiar with, which is that of unitary dynamics, of unitary many-body dynamics. This is an interesting process because this is the very natural dynamics of closed systems, right? You just take a state and you apply a unitary. And the way we model it is by just, saying that this unitary is generated by a time-independent Hamiltonian, and the Hamiltonian is made of local terms, typically, right? Nothing too fancy. And the reason why we know we can simulate it quantum efficiently in a quantum computer is very simple. No, it's basically because we know that we can approximate this type of unitary matrix as a product of smaller ones that end up being a quantum circuit. And the easiest way to do is by trotterization with product formulas, but of course there's many other ways. And in terms of computational hardness, kind of almost by definition, we understand that being able to simulate these dynamics for polynomially large times is the same as having arbitrary quantum computations, right? And here, this is pretty much by definition, I would say, right? So there's some understanding that if we're able to simulate long-time dynamics, then we're doing arbitrary quantum computations, right? And this is why we believe that being able to do this is classically hard. Okay, so now we have this family of what is a family of physically interesting processes, and now I want to put forward a different kind of family of processes, and those processes are the ones that we identify with thermalization. Which maybe you can understand in very vague terms as you have some initial state and you want to drive that initial state to a Gibbs distribution. So I think that until not so long ago, I think all of this, this program that seems so simple for unitary dynamics was still very partially achieved, but I think we're making progress along all these lines. So I hope I can tell you, some things we've been learning now this program for the case of thermalization. Of course, it's far from complete because the story is much more complicated, but I think we're making some good progress. Okay. So maybe just again to keep with a high level motivation, what are we trying to study here? So we're studying well, quantum systems in thermal equilibrium. No, so basically density matrices that are described by e to the minus beta h. This is of course a very important state in physics because many things are in equilibrium, and if we want to do statistical physics, this is the kind of object we're dealing with, and it's not important only in physics but also in lots of optimization problems, for instance, right? So the logic here is that if this is such an ubiquitous state that appears everywhere in nature, so the process of thermalization is so common in physics, then it should also be easy to simulate on a quantum computer, right? And it should be a very natural thing that we are able to simulate these things on a quantum computer. But I would like to argue that maybe until not so long ago, we haven't been able to exactly pin down what is this process. And now we're having a better understanding of what it is. So now the question I want to talk about a bit more is about this process of thermalization, what it is exactly, right? So the question is, how do quantum systems really thermalize? So now I'm going to go into a setting in which I assume I have like this thing is going to be now in the environment, which is already in a Gibbs state, and I couple to it a quantum system. In this case, it's a small system, just a qubit. And the question now is how does this system equilibrate with this environment? And of course, the way we typically model this is with a Lambdadian, with a master equation. That basically, if you wait for long enough, it's gonna drive that density matrix to the Gibbs distribution. Okay, so what is exactly the model that we typically use for this type of question? So in order to introduce this model of thermalization, I need some notation. First of all, my system is going to have a Hamiltonian with some energy levels. And then the system is going to interact with the bath through some interaction Hamiltonian. Actually, I should be using this, right? Yeah, with some operator that acts in the system and some operator that acts in the bath. And importantly, there's a coupling constant between them, right? So through these two things, I can define these jump operators, which are essentially, I take my observer in the system, and I look at the energy eigenbasis, and I just fix a particular frequency and define these jump operators in terms of them, right? So they're called jump operators because they're jumping between different energies with a fixed gap. Okay. So these jump operators are very useful because they allow me to define a master equation. And this is the master equation that is typically called the Davis maps, which is the one that has been used since, I guess, the 70s or maybe earlier, no, in order to understand this process of thermalization in quantum mechanics, right? And the master equation is this one that you've probably seen many times. Is one in which I have these jump operators and I have some weight function here. This essentially comes from the correlation functions of the environment. But importantly, yeah, I have these things here, no, that appear. So this is nice. This is a nice model, and it seems to work very well in many cases. And there's a few ways why we like it. No, and in particular, one reason why we like it is because we know that for sure, if you wait for long enough, well, under some conditions that are not so hard to satisfy, this equation is going to take you. It's going to have a unique fixed point, which is the Gibbs state, and for sure, it's going to drive you to it. And actually, there's something stronger that holds, which is this notion of a quantum detail balance, which guarantees that this property is gonna hold. And this quantum detail balance, the way to state it is the following, right? So we have my generator of my Markovian dynamics, and it has this property. So sigma is my Gibbs state, the fixed point. And what I'm saying is that this object here is somehow Hermitian with respect to some scalar product that is called the KMS scalar product, which is some scalar product between matrices where I have the fixed point here, right? This is just a feature of so this is just an important feature of these generators of the Davis dynamics, right? And essentially it follows from the fact that they have this master equation has this form with these jump operators, and also from the fact that this comes from a thermal state, so that the bath is thermal basically. So from these two properties, we have this KMS scalar product. The thing about this master equation, this Davis master equation, is that in order to derive it, you need to make an assumption. The assumption is that you're in this thing that I'm going to call the ultra weak coupling limit, which essentially means that your coupling constant with the environment is much smaller than all the frequencies of your system. And essentially, what this means for those of you who know about this is that you can take the rotating wave approximation, right? So essentially, what it means is that the dynamics of the system, the natural dynamics of the system, are much faster than anything that the environment does to it. Okay.
Sorry, the previous slide, how was gamma omega?
Okay, I didn't define it, but this is essentially the Fourier transform of the 2-point correlation function of the bath. So you have B of B evolving time times B evaluated in the bath, and you take the Fourier transform. And then this is it. And if the bath is thermal, this is, well, if it's like in a KMS state, this has this KMS condition that guarantees that you have little balance. I don't think I can write. Okay, but anyway, so this is, yeah, it's just 2-point correlation, the Fourier transform of 2-point correlation function.
Beta dependence.
Is here.
Gamma is beta dependence.
Yeah, so but gamma has this property that gamma of omega equals gamma of minus omega times e to the beta omega. So yeah, that's the KMS condition. And that guarantees that you have this property here. Yeah. Thanks for the question. Okay, so now so basically we have this approximation, right? And the question is, whether we can typically take this approximation or not. And this approximation essentially becomes very problematic in the case of many-body systems, right? So I think of a many-body system essentially as that described by a Hamiltonian, which is a sum of local terms, maybe in a lattice. And of course, since I have n particles, the Hilbert space has a dimension which is exponential in the size of the system, right? But the energies are constrained to be in an energy range which is polynomial, right? In particular, is polynomial in the number of interaction terms here. So if n grows, what happens in the spectrum is that I have this spectrum going from the ground state to some maximal energy, and the range of it is polynomial in n, it's linear in n. But I'm trying to fit an exponentially large number of terms within this line, right? So essentially what this means is that you're more or less forced to have a frequency that is exponentially small in system size. And this is typically what's going to happen in many-body systems, right? So now basically we can look at this approximation again. And what you see is that what this is saying is that the coupling with your environment has to be exponentially small in the system size, which seems very, very strange. No, it's something that, this is not something that's going to happen in nature like ever, basically, right? Another way to see, why this is maybe problematic, this Davis, yeah. Yes, yeah.
So you sum over omega there, what's the range of you sum over?
What is the range of this? Yeah, it's basically all of the ones that appear. You have basically each pair of energy levels defines an omega. So this is like a sum over pairs of energy levels. You have to care about the generacies, but yeah.
So it could be 0.
The sum here. Well, I guess, but then your Hamiltonian will be trivial, right? Yeah, it could be 0. Yeah, it could be 0. Yeah, for sure. Yeah. And in that case, yeah, I guess those you don't count. But yeah. So the degeneracies are, if your Hamiltonian is very, very degenerate, maybe it's still a many-body Hamiltonian where this might hold, actually. But typically this doesn't hold, right? So yeah. For instance, when the Hamiltonian is commuting, it has commuting terms, then you can still somehow make this approximation, even if you're in the many-body setting, actually. Partially because of the degeneracy. Okay, so but anyway, another reason to see what is problematic is to kind of go back to these jump operators and to this definition here. So these are very complicated objects in general, right? And the way to see this maybe from the quantum computational perspective is that in order to encode these operators in a quantum computer, for instance, you will need you will need to run dynamics for very, very long times, no? Which essentially means that you need a very high precision in energy, right? Because you need to resolve this type of frequency, which may be very small, right? And if you think of this definition of jump operators, this is like you can write it in terms of a Fourier transform of a time-evolved observable. And in the Fourier transform, you essentially have a very long time that you have to take in the integral in order to be able to generate these operators, right? And these objects are also extremely non-local. So it seems very strange that these operators, these jump operators in the many-body setting, are the ones that nature is choosing to thermalize your system. No, it's not clear that when you have a many-body system coupled to a bath through a local coupling or something like this, it's not very clear whether these operators are the ones that are going to emerge in the description of that process, right? And it seems that this is not what's happening really, no? So what this means essentially is that these Davis maps, the usual models of thermalization, do not seem to work in the many-body setting, right? Okay, any questions about this? Okay, so I want to move gears a little bit and talk a bit about algorithms for thermalization. in particular quantum algorithms for thermalization, which I think, since we have this problem in the open system setting of how we describe thermalization, we also had some similar problems for understanding how to construct good quantum algorithms for thermalization. And maybe historically, it's interesting to talk about what is the classical template that we want to mimic when we build the quantum algorithms for thermalization. And the classical template is a very successful classical algorithm, which is the metropolis sampling, right? And the metropolis sampling, essentially what you do is you pick up a configuration of your spins, for instance, where you can measure the energy, and then you update it, right? So you change some spins, and then you measure the energy again. And then you accept or reject that new sample of your spin configuration. And the probability with which you do this is this thing, which has to do with, well, this is the usual metropolis weights, but it's basically chosen in such a way that it ensures that this detailed balance condition also holds classically, right? So for this classical metropolis, you need these few things. No, you need this detailed balance to hold, which is guaranteed by the choice of the transition matrix that you choose in your samples, and you also need to be able to update your system, no? and efficiently implement those updates. And in the classical setting, this is easy, essentially because your eigenstates are product. So you can just flip spins and you get a new configuration of your metropolis samples, right? However, if you want to translate this to the quantum setting very naively, of course, this thing of the eigenstates being product does no longer hold, and in fact, the eigenstates are very complicated, so this becomes problematic. However, there was a nice algorithm a few years ago which seemed to be the analog of quantum metropolis, but it didn't have. I don't think it had very good efficiency guarantees, and in fact, I've heard from recent advancements that the version of this algorithm in this paper requires some sort of phase estimation algorithm that is like way too precise or something like this. So it was nice advancement, but it did have some problems basically, and it had problems also along the lines of the problems of the Davis generator also, right? Roughly speaking. After this, I mean, of course, this is an old algorithm already. After this, people were working on various other types of algorithms. Most of them actually had exponential guarantees, even in cases where it should be. We expect that it's easy to prepare Gibbs states. They still have exponential guarantees. And just to give you some quick summary of papers that are more from more or less 4 years ago and older, right? They can be more or less divided into 3 categories. Those that have to do preparing purifications, and other ones that mimic dissipation in some way, or also variational ones, right? And of course, here there's some very nice works, there's some very nice ideas, but I think they were not quite capturing, the real thermalization process, right? And the way nature seems to be thermalizing. And if you were able to do this, then you were able to come up with a better algorithm. And I think none of these works kind of got there fully, let's say. So I think we were missing something with this, with this target of mimicking thermalization and producing Gibbs states in a quantum computer, right? And what is nice is that there's been some nice progress about this, and there's this paper that I want to give a fair amount of credit to, which is this one by these authors from November 2023. And essentially, what they do in this paper is they construct a new Lindbladian, a new master equation, which is different to the Davis one, and it has 3 properties. Okay, the properties are that this Lindbladian has jump operators that are quasi-local, so they're simpler than the ones that from the Davis maps. Not only that, they're not only quasi-local, but you can also efficiently implement them on a quantum computer. These 2 things are very closely related, but they show that they both hold. And the nice thing is that these 2 things hold, and at the same time, your Lindbladian has this exact detail balance. So you're guaranteed that you converge to the right state, to the Gibbs state, right? And there were maybe previous quantum algorithms that had, for instance, these 2 properties, but not this one, right? So it was not clear whether you could satisfy these 3 things at the same time. And this is what they achieved here, right? And essentially, the way they do it is, in hindsight, I guess, a bit simple. Is that in the jump operators, you define them in a slightly different way, and basically you have to introduce a function here, some sort of filter function, which you can take it simply to be a Gaussian. And now the quasi-locality essentially means that, well, essentially is implied by the fact that this function quickly decays, right? So if you get rid of this, you recover the Davis jump operators, right? And what is interesting and what was a bit non-trivial was that you can do this and at the same time keep this exact detail balance, right? And for this, you have to be very careful about how you choose this and a few other things about the Lindbladian. I'm not writing it fully, but it is possible to do this. And this was like a nice, I think, quite nice piece of progress, let's say, no? But the thing is, this constructs a Lindbladian, But what was not fully clear, although it was more or less expected, is whether this is something that actually corresponds, this Lindbladian, whether it corresponds to a real process. By a real process, I mean whether it corresponds to a system weakly interacting with a bath. Okay, so I have the setting from a few slides ago, but now I don't want to make this rotating wave assumption essentially. So I want to start with some system bath interaction Hamiltonian, right? And I want to know if something like this, the process described in the previous slide, emerges. And why do we think this was maybe possible? So, well, because people have been working on this, and there was some previous works that were kind of more or less telling us that this was possible, right? So there's something that maybe some of you have seen, which is the derivation of the previous master equation of the Davis, right? For instance, in this couple of books on open systems, that they're able to derive a master equation from first principles with the rotating wave approximation, right? And it has this notion of detail balance. However, there's also more modern derivations of master equations, which are different to the Davis ones, that do not rely on the rotating wave approximation. And here, I think there's at least these 4 works. There's probably others, actually. So we knew already that there were kind of master equations describing the open system dynamics, contact with a thermal bath, that did not rely on the rotating wave approximation. However, none of these works had this property of the detail balance that I mentioned earlier, which is important to guarantee that you converge to the right Gibbs state. So essentially, we had some pieces, kind of disjoint pieces, right? But in the end, we didn't have something that we wanted, no? So because essentially we didn't have a master equation that we could derive from first principles that did not rely on the rotating wave approximation, and that it had exact detail balance, no? And moreover, actually, I mean, something we also like as mathematical physicists is to have some sort of rigorous accuracy bounds for this master equation. And for instance, well, most of these works don't typically have rigorous bounds on how close the master equation is to the real evolution. But for instance, this one did. Actually, this one is very nice in that respect. And also the Davis one. But the question we have now, and the question that is very strongly suggested by this master equation, is whether we can have all those, right? So now we have a target. So we know the master equations with the properties that we want exist. So the question is whether we can kind of derive it from first principles, right? And yeah, this is a question that we were able to answer recently. So Matteo worked on this for quite a few months, and in the end managed to crack the code, I guess. So what we can do is we can derive, again, for first principles, a master equation, which has the following properties. It has quasi-local jump operators, so it does not rely on the rotating wave approximation. It has exact KMS detail balance within the approximations that we take. Also, it has the nice property that it approaches the Davis one in the limit. So if you're in this setting where you can take the rotating wave approximation, you still recover this. And also we have some rigorous error estimates. And what that means is that we can take the actual evolution of your system weakly coupled to a bath, and our master equation approximates that evolution with an error that grows as follows. It becomes small when the coupling becomes small, and it grows linearly with time. And also you have, well, the prefactors here have to do essentially with how quickly your bath dissipates the information. So if your bath is very Markovian or very, very chaotic or whatever, this number is very small. And also with the temperature, because this has to do with the detail balance property. Yeah.
Sorry, that's for me to digest. So
yeah.
like in the Anthony Chen's paper, what's the connection of this work to the Chen's paper?
Yeah, so that's in the next slide, actually. That'll become clear in the next slide. Yeah. Yeah, so maybe I answer this in a second. Maybe just to finish this, I wanted to say that, for instance, this paper that has some nice rigorous bounds also on this distance had some exponential growth in time. So we were able to improve from an exponential to a linear growth in time. And this actually, if you look at the literature on many-body open systems, the fact whether this kind of master equation existed was a bit of an open problem, I would say. And in fact, for instance, if you look at this review, which is relatively recent, there's I don't know, there's some section somewhere where they say that we don't yet have a model of many-body thermalization that drives you to the many-body Gibbs state, because in much of the physics literature, the models they were considering was, for instance, single qubit depolarizing channel or something like this, merged together with the unitary dynamics, for instance. So, which doesn't converge to the exact Gibbs state, right? So it seems that this kind of Lindbladian is the right model that drives you to the Gibbs state. And to answer that question, maybe I can show you what this Lindbladian is, just by showing the jump operators. Okay. So the Lindbladian we construct that we know approximates the real dynamics when you're weakly coupled to a bath is it's as follows. We have the jump operators, and the jump operators have this form. And essentially, this form is a particular case of the Chen Limbladian. Where now, well, I'm writing this in terms of frequencies instead of time, but you could take the Fourier transform. So I have this Gaussian here, which you have to understand as well. I guess I have a Gaussian, and then this thing which has to. This is again the Fourier transform of the correlation function of your bath. So this function is somehow the analog of this exponential. Well, its Fourier transform is the analog of this exponential, essentially.
So FT has no like correlation function information, but you're saying the G has a.
Yeah. So well, the thing is, this f of t, you have some freedom of how you choose it in the algorithm, and this is kind of the simplest choice. But there are more complicated choices.
Actually, what does sigma E decide here? You show sigma E as some sort of.
It's the width of the Gaussian, yeah.
But like in the space or.
It's
Does it decide the localness of the jump operator?
Yeah. In time, yeah. But this is like a free parameter. And for instance, how long does it take you to simulate this Limbladian has to do with sigma E. So at this level, it's a free parameter that you choose for when you want to implement the Limbladian. For us, we were forced to take in a fixed form because essentially the Gaussian depends on the coupling constant. Yeah. So for us, the profile has to be this, because you have the coupling and then you have the interaction with the environment. So the analog of sigma E for us is something like the inverse of the coupling constant, essentially. But really, you can think of this pretty much as a particular example of a Chen Limbladian. And with their simulation techniques, you can also simulate this master equation, I believe. Yeah. So maybe just to sketch how what we do to get here, we do very standard things that were already in previous papers, but kind of put together, right? You have to assume some things about the bath. You have to assume that your system and bath are initially uncorrelated, which you need to do in order to get a CP map. You have to assume also your bath is quadratic, so you have some sort of Wick's theorem, although I think this can maybe be relaxed. And also you have to assume something about how about your bath, about whether these correlation functions decay and how fast, essentially, right? And in the proof steps are, I don't want to spend too much time on this, but the proof steps are essentially the standard ones, no? So Born Markov and the Redfield and so on. But the difference now is that we are able to put some rigorous bounds on this, on how good these approximations are. Yeah, question.
How is it different from there's a work from Dima on dealing implant function, on using the implant function and figuring out what cluster equation is. And they also use a quadratic map. And are there some?
I'm not familiar with this work, but is this so the from in the Wick coupling setting with a bath or okay, I'm not familiar with this paper. Yeah, well, this is essentially a very similar approach to these other papers. Oops, this actually these two mostly. Yeah, for instance, yeah. I think this is not the fundamental assumption, but it helps a lot actually. So.
And also, your system is now anybody. So
yeah, it could be. I guess what I'm thinking is that you have a very large bath and you have a large system, but you're locally coupled. The bath and system are locally coupled to each other. Yeah.
Can I also say the question about your Wick theory? Do you have some special region for frequency omega on your Wick theory?
What? So it was.
Maybe there's something you have the quadratic frequency. How about you can look at this kind of exponential large T of lambda? Okay, you would get some constraint for preserving Wick theory. Do you have this? Do you understand that region?
I don't know if I understand so this is something we assume about the bath, not about the system.
Right. So then you have the push back to your concern of the lambda. You push back to the previous slide. Look at this limit. There's there is a back limit of the lambda equals the much small, right?
Yep.
in that region, you have the freeform ubiquity.
For the Davis, to derive the Davis. Yeah, because Davis also did this, I think. That's why. Yeah. So I suspect so. Yeah. So you're saying, I mean, so you're saying that this assumption is also necessary for Davis.
I think that beyond that, you have some violation of the ubiquity. What happens?
Okay. Yeah, I don't know actually. I mean, so you say if the weak theorem doesn't hold, what happens to this derivation?
You have the serious problem on the violation of the ubiquity.
I see. Yeah. I don't know. I remember Mateo saying that he seemed to think it was not. I mean, you could get around it by some other assumption on the bath. Like maybe if you're. I mean, I guess you need some sort of simplification of your higher order correlation functions, right? So, which maybe holds in some beyond Weak's theorem in some way, but I don't know. So, I guess for us it was just simple to assume this and then go with it. So one extra step that was not in previous works and we had to do is introduce this. I mean, we had to consider this notion of approximate detail balance, which we had a target because we knew what this looked like essentially from this Chen et al. Lindbladians. So this was an extra step in the proof that was not present in previous proofs, and that's, for instance, why we have this error term that depends on beta. Yeah. Yep, this. No, this is no. The actual Hamiltonian, we don't. You can introduce it. This doesn't matter. This is just some. This is some term. So this is this. Yeah, I guess. Yeah. With the hyperbolic tangent and so on. Yeah. What's funny though is that somehow the contribution of this is very small and actually it's kind of within the approximation error. So it's like we here. To prove this distance from this to this, we make this error, and somehow you can just, I mean, this lamp shift term kind of is almost a bleeding actually. So we can just introduce it for free pretty much. So the difficult part was in the other part. So I mean, for them it was very important they had this lamp shift for the exact detail balance, but actually it seems that it's not the most important contribution physically, let's say. Yeah. Yeah, so this is the Fourier transform of the square root of the bath correlation function. So this is what comes from the bath, essentially. And this has this KMS property. Yeah.
Very stupid, but so you show the Lindbladian jump operator from the Chen speaker, and now now your goal is trying to get it. Derive it starting from the actual system that.
Yep. Something that looks as close to it as possible, and I think we get this essentially, and this is really as close as it's gonna get. Yeah.
And then I guess exactly realizing this Lindbladian from Chen speaker is possible, but you're showing some, I guess, a physical example which can approximate that Lindbladian.
Yeah, I mean, yeah. So the thing is, of course, the physical Lindbladian is going to depend on the bath. And maybe if your bath is simple enough, you're going to reproduce the simple existence of the Chen algorithm, which is with the Gaussian. But for this, you need a specific bath, what's the word? A bath response function, right? So in general, you can have other response functions, right? I give you different Lindbladians, which will still have all the nice properties because they still have the KMS, the balance, and so on. So it's just that you're not going to get a nice Gaussian profile. You have something else.
So what kind of so here you have A had omega star instead of that A in that Chen speaker. What kind of S would realize, I guess, that?
Well, it depends because I mean I think the framework is quite general, so you can put a lot of filter functions. Actually, there's quite some flexibility there. So I suspect this may be a large class of baths. I don't know how large though. That's certainly a good question. The thing is, if you have somehow access to this function and to the time version of this function, so to the Fourier transform, if you have some sort of quantum encoding of it, you should be able to simulate the Lindbladian in the quantum computer. Because in the Chen algorithm, you just kind of need some encoding of the filter function. So as long as you have that, you can simulate the Lindbladian basically. So actually, this is going to be in one of my next slides also. So maybe just to conclude this section, I just want to make the case that we're kind of making progress in this first point of my first slide. Now, how do we model this normalization process? Right? So now I can move on to the next part, which is what is the quantum algorithm that sorry.
There's error bubble.
Time
dependence.
So I'm actually seeing the steady state of the actual dynamics.
Mhm.
That's kind of unclear how to
Yeah, that is true. That is true. Yeah, so there you'll need, I mean, you will need a good trade-off between the coupling and your mixing time. Yes. Mhm. I mean, what could be the case that you kind of always go to something that looks thermal, but it's not exactly thermal, right? And this could be compatible with that, for instance. Yeah, that's maybe what happens actually in practice. Yeah. Hmm. Yeah, so my impression is that, yeah, I mean, I think it's all in the approximations, right? So I think they may probably say you shouldn't get to the Gibbs state, but you probably you can more or less guess that you get something that should look like the Gibbs state locally, maybe, no, or in some way should look like the Gibbs state, no, with the right energy and with the right entropy and so on. No? But I guess what we're saying is that you also, I mean, you can, with some further approximations having to do with beta, you can really get exactly to the Gibbs state, no? And I mean, maybe in the end, I mean, I think in the end it's all compatible. It's just that we have to make us a large. So maybe what this means is this kind of tells you how far these previous papers were from actually achieving the Gibbs states, right? In one norm, maybe, so I will guess that if you don't look at one norm but at something weaker like local expectation values, maybe you can get rid of this error. You can make it much smaller. Or something. Yeah. Okay. Yeah. So maybe I can move on to the implementation of this. I mean, I'm not going to talk too much about it, but I just want to mention that I mean, one of the main results of this paper is that you can implement this general Lindbladian. Well, actually, I'm showing the Gaussian here because it's the simplest one. But you can simulate this Lindbladian, and the computational cost in terms of gates is linear in time and also linear in this number that I was showing here. Somehow the width of your filter. And the way they show it is by some explicit algorithm, which has, I mean, it's this one here, but essentially it involves some encoding of your filter function and some block encodings of your jump operators and so on. And you have to take some sort of, Fourier transform in your algorithm. And what this is essentially some sort of block encoding of a single step of your Lindbladian. But really, this means that you can simulate the Lindbladian reasonably efficiently, right? So this is a bit of a complicated algorithm within this block encoding picture and so on, but people are working on making it simpler. And there's been some recent progress on this question. And in fact, there was a paper from maybe a couple of weeks ago where they have some quite interesting simplification. I don't remember exactly with which guarantees they have a simplification of this algorithm, but I think it's interesting work. That's why I wanted to mention it. But anyway, so just going back to this, what I want to say is that we have our Lindbladian, roughly speaking, was one in which, I mean, up to some details, I'm simplifying things, was one in which this parameter depended on the coupling constant, okay? On the inverse of the coupling constant. So for simulating our Lindbladian should more or less take this kind of computational time. There's another convenient choice which I want to talk about, which also simplifies calculations, which is one in which you take the width of the Gaussian to be dependent on the temperature. This I'm going to call the algorithmic Lindbladian. This is another convenient choice for what I want to say next. So this is nice because it tells you for how long you have to simulate your Lindbladian. What's the cost of simulating this your Lindbladian for like some amount of time? Okay. But now what you want to know is, if you want to actually reach the Gibbs state, so the steady state, how fast, for how long you have to run it, right? So what is the speed of convergence of this dynamics, right? And this is the next result that I want to talk about, which is in this paper with Gibbs and Daniel. And essentially, we have a result on rapid mixing for high temperatures. So what we show is that the one norm, so the distance between your Gibbs state and your time evolved state, decreases like this. No? So it decreases exponentially in time, and there's a prefactor which is polynomial in n. And this is pretty much optimal, actually. You cannot really do better than this in terms of the scaling with n. So we have two conditions. The first one is not very strong. Essentially means that your Hamiltonian has to be local, the Hamiltonian of your system. And really what we need is that you have a Lee Robinson bound in your Hamiltonian. The second assumption is a strong one that we would like to weaken, is that you have to be in a very high temperature regime. Okay, and we have some explicit expression for what this means exactly in terms of parameters of a Hamiltonian. Yes.
So in some slides before, you had a result that the deviation is also increasing linearly with time.
Mm-hmm.
But like, what happens if you use that Lindbladian?
Yeah.
You can actually converge to the Gibbs states, or
That's what I don't know actually. So things have to maybe work out nicely, you know. So you have competing things, and I don't know if they always work out nicely. They may work out in the sense that you approximate something that looks like a Gibbs state, but I don't know if in, you know, the thing is, I don't know if really in nature you kind of always go to the Gibbs state. You maybe sometimes just go to something that looks like the Gibbs state, but not the exact Gibbs state, no. So this is more for the quantum algorithm, no? And the quantum algorithm, we know it goes to the Gibbs state. So yeah, so this is, I mean, this is a bit subtle, I think. But
another question is, if beta is small enough, you may well just approximate the state using maybe some classical density traits.
that that is true.
The question is, like, if beta is smaller than beta star, maybe you can spoof quantum Gibbs state by just using a classical density.
So for sure, so the regime of high temperatures that we reached so far is still within the classical simulable regime, I would say. Yeah, this hopefully at some point we manage to overcome that actually. Question, yeah.
Not sure about this type. Does that mean, so for example, if I have some component with inverse polar gap, and if I run your algorithm, does the state converge to some state that's close to the ground state?
No. So I mean, this is the opposite then. This high temperature means that beta equals 0 is. So if beta is 0, you're in the infinite temperature, so the identity matrix is your state. So I mean, the gap of the Hamiltonian does not matter here. So maybe I go to the next slide because something might become clear here. So maybe I want to give just a proof of sketch, of how we prove this actually. The first thing we have to do is something that maybe I've already hinted at, which is to show that the jump operators are actually quasi-local, right? So we just have to take the definition of the jump operators from Chen with the filter function, and kind of make it a bit quantitative, what this means, And if you just apply the Robinson bounds in the obvious way, what you show is that these jump operators are well approximated by something that lives on a region of radius L with some exponentially good bound. This is just the Robinson bound, okay? Now we have to make an extra assumption, which is that the jump operators we took initially have to be like nicely behaved. And essentially the most natural choice for us to take was for them to be like all the single body Paulis. And actually the reason for this is that something we really want of the Lindbladian is that in the limit of beta equals 0, this becomes a very simple Lindbladian and we know how to understand. And this Lindbladian is essentially the depolarizing channel, okay? And this is also why I wanted to take this Lindbladian here is one for which the filter function depends on beta, which is what I did here, okay? So I'm looking at this algorithm, at this particular choice of Lindbladian now. And the reason for this is again, is really just that, no? We want to be somehow converging in the beta equals 0, we want to converge to the polarizing channel. The polarizing channel, we understand very well. We know that it mixes very fast to the steady state. So essentially what we need to do is we need to do some interpolation to the polarizing channel, right? So what we need is essentially that we need to understand in which way the Lindbladian is a quasi-local perturbation of that depolarizing channel, and then apply some sort of continuity bound for the rapid mixing property. And this continuity bound is the non-trivial thing here. And essentially, you have to come up with the right kind of quantity to bound. No? And in this case, it happened, and this is just some magic that Gibbs came up with. Actually, I had no idea about this, but there's something called the oscillator norm from a classical paper of Struck and Zegarlinsky in the early 90s. So this is a norm that is a bit funny, and essentially is defined in this way, with some partial traces. And if you analyze how far the Lindbladians are somehow in this norm, if the distance in this norm of your channel to the polarizing channel is small enough, then you can infer rapid mixing essentially.
Is it something like, I guess in some sense, like those depolarization channel Lindbladian is like the fixed points with a, I guess, nice gap, and you're assuming that adiabatic, you're assuming adiabaticity, that's actually proven using.
Yeah, it's something like this, no? So the polarizing channel is like a nicely behaved point. This is stronger than the gap of Lindbladian though. So but the idea is that essentially, yeah. So we have this nicely behaved point that converges very well, and somehow this property is robust to errors, and the error here is introducing beta, introducing small. These are the errors essentially, the tails of this jump operator. Yes. And from this, essentially, because we have to apply this kind of continuity bound, this is why we're bound to high temperatures, because we only can get so far, essentially. Yep. Yeah, so I guess hopefully with these two results, I've convinced you that we also made progress along these lines, right? Because from the Chen et al. Paper, we have some understanding of how to simulate the Lindbladian, and at least for very high temperatures, we know for how long we have to simulate the Lindbladian in order to get the Gibbs state. So maybe now I'm not doing super well on time, but hopefully yeah, should be okay. I can maybe give a few words of a general, I guess, computational problem, which is the problem of preparing Gibbs states with a quantum computer, right? So what do we know about the computational complexity of this problem? And what is nice is that this problem somehow, you can understand it in terms of the ranges of beta you can reach. Okay. So beta equals 0 will be the trivial point of the identity matrix, and this will be the ground state, right? So okay, so what do we know about this? We know a few things. So from what I've told you, now we know that for some regime of high betas, we can prepare the high temperature Gibbs states efficiently on a quantum computer. Okay, and this also followed also from a different work of Bakshi et al., where they have it's a very different way of preparing the Gibbs state, but it also works at high temperatures. On the other hand, we know that for very low temperatures, the problem of preparing Gibbs states is going to be QM hard, so very hard even for quantum computers, right? And essentially, the reason is that for very low temperatures, then the Gibbs states approximate ground states, right? And there's a question about whether this hardness also holds for higher temperatures, right? Maybe going all the way to order 1, actually. But another thing we know, and this is already the case for classical systems, is that sampling from Gibbs distributions, even at temperatures that are order 1, at some point is going to become NP hard. And this also has to do with thermal phase transitions, I believe. So at some point, we're not going to be able to sample efficiently, either quantumly or classically from Gibbs distributions, at least in some two-dimensional models, perhaps. No? There's also some nice works showing that sampling from Gibbs states at constant temperature is something that seems to give some sort of a quantum advantage. This is there. Well, I forgot to mention another work by James Watson here.
Quantum advantage in what sense?
In the sense that in the same sense of IQP circuits. So random sampling. Essentially, what this paper shows is that sampling from the Gibbs distribution gives you you can distill samples from an IQP circuit, essentially. So yeah, advantage in the sense of sampling tasks.
So actually, below certain temperature, the randomness of the Gibbs state is something that cannot be mimicked by a person classical circuit.
That seems to be, yeah, I mean, for sure at some point, yeah.
It's not very utilizable quantum advantage though, right?
This no. I guess for that, what we would like to know is maybe so I guess we have this understanding of when is quantumly efficient to prepare Gibbs states and when is classically efficient. And so far, we don't have. I mean, it could be the case that the quantum algorithms can reach lower temperatures than the classical ones in the general case. This is a possibility that we don't yet know. No, I think I will conjecture that this is the case. No, that you have some Gibbs sampling task at low temperatures, which are not super low because you can reach the NP hardness regime, but maybe there's some intermediate regime here where you have quantum advantage. I think this may be still possible. Yeah, and yeah, hopefully. The problem is that the efficiency proofs both for quantum and classical algorithms at the moment are kind of too similar, because we rely a lot on perturbative expansions around the beta equals 0, actually. Yeah.
You know how close whatever your bound is for high temperatures needs to the bound for the sudden negativity?
From what, for?
This finite temperature bound for a sudden negativity. Are these?
I think in some parameter regime, I think they're kind of incomparable, but in the sense that there's some parameter regime in which one is better than the other, but I think this one is a bit better for its lower temperatures. I think I'm not 100% sure actually, because they don't complete this. They don't state the temperature in this paper super clearly. But I think if you look at some reasonable, 2D Hamiltonian or something like this, I think theirs is probably better. But yeah, I'm not 100% sure. I think it's safer for me to say that theirs is better, so I'll just go with that for now. Yeah. But it's a very different method, so maybe some improvement either way. The balance could change maybe. Okay, so now I want to change gears a little bit and talk about what you can do with these Gibbs samplers in terms of quantum computations, okay? So now I want to answer a different question, which is the following, right? So if now we're not in the general case of Hamiltonians, but maybe we can choose H adequately while having access to one of these Gibbs samplers. So the question is whether by doing this, we can solve interesting computational problems. And this is the philosophy here is essentially the philosophy of some previous papers where they try to do quantum computations by dissipation. And this is maybe the most well-known paper along these lines, where they come up with a Lindbladian that if you're able to run it, you can simulate arbitrary quantum computations. And also, for instance, this paper is, I mean, it ends up being very close to what we do. And in fact, we took some of their ideas, which essentially shows that through dissipation, you can also through dissipation and some sort of optimization, you can also reach, well, you can perform arbitrary quantum computations, actually. Okay, so what is the logic here? So I want to build a computational model that has to do with these Gibbs samplers. And I think it's nice maybe to talk about, again, of an analogy that you all are familiar with, which is the model of adiabatic quantum computation, okay? So in the adiabatic model of quantum computation, we have some things that we understand well, right? So we know that if you run the algorithm well enough, you produce a state that has low energy or low temperature, right? Just by running it slowly enough. We also know that the adiabatic algorithm is implementable in a quantum computer just because you can characterize the adiabatic dynamics. We also know that this model of computation is universal for quantum computers. And the way to do it actually is from this classic paper of Haronov et al. The way to show it was by showing that you can prepare the Feynman-Kitaev history states efficiently with this adiabatic algorithm. And we also know in these adiabatic schemes that if you have some sort of gap, then you have some efficiency guarantees, right? So I would like to argue that in this paper of Chen et al., they showed the first two things because they have a Lindbladian that has detailed balance, so it goes to the Gibbs state. So you know that if you can take beta to be low enough, you're going to reach a state with very low temperatures. Beta being a parameter in your algorithm, in your Lindbladian that you can tune. No? If you can tune it to be large enough, then you can go to low energy states, right? And they also showed that these Lindbladians are implementable on a quantum computer. Okay, so in order to have a good model of computation that is equivalent to quantum computing, we need to solve these two questions, and this is more or less what we did in this other paper. So I talk a bit more about this. So the result is the following, right? The result is we define a class of problems which we call Gibbs QP, which is essentially the class of problems solvable with Gibbs samplers when you have access to Gibbs samplers, and you need to also have access to very low temperatures. So temperatures that are actually polynomial in system size. No, I'm assuming here that your computation has like poly-sized circuits essentially, right? And not only you don't only just need access to this Gibbs samplers for low temperatures, but you also need to do some sort of measurements at the end, actually. That's part of the computational model. But if you're able to do this, the kinds of computations you can do are equivalent to arbitrary quantum computations, polynomially sized quantum computations. Yeah. In which this one?
They only show that their Hamiltonian is
No, so they show that you can simulate the Lindbladian efficiency in a quantum computer. So that's one of the directions, but you need the opposite direction, right? That you can simulate, if you have access to the Lindbladian itself, you also can simulate an arbitrary quantum computation, right? So one direction they do, not the other one. For the other one, you need to do a bit more, which has to do with these history states. Okay, so what's the idea here? So the idea is that we have a very famous paradigm in quantum complexity, which is this business of Feynman-Kitaev history states, right? What is this? This is essentially local Hamiltonians that you can construct with nice locality properties. Some people have worked on improving this for many years. But the nice feature of this is that they have a ground state that is able to encode an arbitrary quantum computation. Okay, so the ground state of a Hamiltonian that you can design has the following form. It's as follows, right? So you have two kinds of registers. One of them is the clock register, and the other one is the computational register. So if you have access to this state, this is any polynomially sized circuit. So if you have access, for instance, to the clock, you have access to any point of the computation, right? So this will be a particular point of your quantum circuit that you're implementing kind of gate by gate, right? So the idea here is that if you have access to copies of this state, you have access to an arbitrary quantum computation, right? Because you have access to any intermediate point of the circuit that you want to implement, right? So being able to generate the ground states of these Hamiltonians is the same as having access to arbitrary quantum computations, right? And for instance, for the adiabatic model of computation, what they showed is that you can prepare the ground state of this Hamiltonian efficiently with the adiabatic with an adiabatic evolution, essentially by showing that this Hamiltonian has a nice gap. Okay. So the question now is whether we can produce something that looks like these states, but dissipatively, right? So introducing some temperature essentially, and whether we can go to that state with these Gibbs samplers. And this is what we try to achieve, right? So now we have a model in which if you start with some initial state, which could be the identity, doesn't matter, and you run it for long enough. I mean, that long enough has to be polynomial times, of course. Then you reach a Gibbs state, and this we know that you do because of a detailed balance condition. And if you're at low enough temperatures, then this Gibbs state looks a lot like the ground state. Of course, the temperature has to be very, very low, right? And of course, the way we construct this Hamiltonian is in such a way that the ground state looks like one of these history states. Okay. In fact, I think the history state we end up taking is the one from this paper that I mentioned earlier. This one here. So the history state I think is the same one as in this paper. So then essentially to prove this BQP hardness, what we need to show is that we're able to efficiently do this. No, whether the time you need to run this Limbladian for is nice. No, it's kind of polynomial in the size of the circuit. So in order to show this, well, not only that, but also we need to show that for betas that are like not too large, we're reaching a Gibbs state that has a good enough overlap with the ground state. Okay, so maybe just to put this into context a bit more, what we're showing essentially is that if you choose the Hamiltonian a bit carefully, and you're able to reach this regime, not for general Hamiltonians, but for a specific one, then here you're reproducing arbitrary quantum computations, right? But I mean, this is a bit different because we're choosing really the Hamiltonian very carefully. This is not a general Hamiltonian. Okay, maybe I just give you the proof sketch of this in the last few minutes. So essentially what we need to show is that the Limbladian, the Gibbs sampling Limbladian for this Hamiltonian is nicely behaved. So what do? We essentially do perturbation theory in a few ways. So the Hamiltonian of the history state has two parts that are very different, the one about the clock and the one about the circuit. And this one somehow is the complicated one because this has the information about the unitaries, and this has only the information about the clock, which is simpler. So essentially what we do is we study the gap of the Limbladian only for this Hamiltonian, and also in the limit of infinite temperatures. So when your Limbladian wants to reach the ground state of this Hamiltonian. This is a very simple case, and for this you can compute the gap pretty much exactly, and the gap is nicely behaved in this case. So then we just have to introduce some perturbations around it. First of all, then we show that here we have infinite temperature, but by continuity in beta of the gap, we show that the Limbladian and the gap behave nicely for beta that is large enough. No? So beta polynomial in n. So notice here that we're perturbing around beta equals infinity. Yeah? And also by continuity in the Hamiltonian parameters, in particular in this parameter, we can also show that the gap still doesn't close, even if you introduce this information essentially, right? So if you only consider this, you have a large gap, but we're saying that if this is like not too large, then the gap also doesn't close, right? And this is a bit of a fine balance that you have to consider for this to work, and you end up having to take this to be a very small perturbation actually. But things work out in the end. And essentially, what we do is that with this we guarantee that you converge your Limbladian in polynomial time converges to a Gibbs state with a very low temperature, and this has a high enough overlap with the ground state, right? So it has polynomially large overlap with the ground state, and because it has polynomially large overlap with the ground state, and your Hamiltonian here is frustration free. This is an ingredient that not all the history states have, but this one did. By measuring the energy of this Gibbs state, you can certify whether you're in the ground state. So, and then basically you have to keep generating these Gibbs states, and then measure them until you reach the ground state. And once you reach the ground state, you have access to the arbitrary quantum computation. So this is how you reach BQP complete, let's say, computations, right? So you just repeat until you succeed to measure the ground state, and that's it. Okay, so actually with this, I want to make the case that we have some better understanding about the computational hardness of Gibbs samplers. Although of course this is this is maybe only one thing. No, this is only for very low temperatures and so on. So there's also some more questions to be answered along these lines. I will say, right? Okay, so maybe just to wrap up a bit, I wanted to make the case with what I was saying that there's been recent nice progress on essentially preparing Gibbs states in quantum experiments, and I was showcasing this business of quantum algorithms for preparing Gibbs states and some better understanding that we have of these tasks. And another thing I want to mention is that there's been a lot of nice progress also on a different task that is very related, which is Hamiltonian learning for Gibbs states. So there's been like quite nice theory work and also experimental work in this task, and they somehow complement each other. So what I want to make the point is that somehow verification for experiments involving quantum Gibbs states seems to be more efficient than the general case, right? So these are good news, and this means that I think that there are some good opportunities for quantum computation of basically quantum statistical physics, right? For instance, one thing that is an interesting avenue is to see if these algorithms that I was talking about, and also maybe some of these learning protocols, whether they can be done in the near term, for instance, right? And as I mentioned earlier, people are already thinking about this, right? And I think one avenue that this opens up is to study essentially, to study and to verify thermal quantum phenomena. No? So now there's maybe a lot of quantum statistical physics that we may be able to probe with quantum computers, and I would like to know what is the most interesting things that we can study here, right? And I mean, I have some examples of things that maybe are interesting to study now in quantum experiments, and yeah, who knows? Maybe you can do them with these algorithms that I was talking about, right? And yeah, with this, I want to conclude actually just flashing the conclusions of the papers that I mentioned, no? And with the archive references. And yeah, just to mention some open questions. One important one, I think, is in what regimes do we have efficient thermalization, and whether this goes beyond the regimes of classical simulability. This is, I think, is still open, and I think there's still room for some nice results. And again, whether these algorithms can be implemented more easily, and whether maybe there are more heuristic approaches that still work very well in practice, right? And also, more of a physics question that maybe some of you are able to tell me about, whether there's some, nice models that we would like to study, or nice, interesting statistical mechanics problems that we can maybe study with this type of algorithms, and hopefully there'll be a lot of these things to study in the future, and we hope that this type of algorithm helps in discovering, nice thermal physics, essentially, nice thermal quantum physics, right? And yeah, with this, that's all I had to say. So thanks a lot.
So I have two questions. The first question is whether it's possible to make thermalizing Lindbladian to be spatially local if the Hamiltonian is local.
You mean strictly local without the tails? Or
yeah, essentially.
So because now with the tails, and with the exponential tails, we know that it works. But so if you want to make it exactly local, I think you wouldn't.
Or can you make a bound something like if you have a range, if you want to have a range to be like a D cutoff, then can you establish a bound that maybe
what cutoff? Sorry,
like your jump operator is spatially strictly local with like range D.
Okay.
Then it can only realize the density matrix up to some exponential and minus D error or something. Is it possible? Is it immediately possible, or do you think you?
So for instance, if you cut off the jump operators, you have some approximate Lindbladian. And then there's a question of if you implement an approximate Lindbladian, whether you go to something that is close to the fixed point, and that depends on the mixing time. So if you have fast mixing, then maybe you can make it work. You go to something that is approximately the right state. But I don't know if in general that's gonna work actually. I mean, I suspect that you probably it's kind of the same story. You maybe go to something that effectively looks like what you want, but maybe not exactly that, right? So
I see.
Yeah. So in practice, what you say is probably the case. In theory, I don't know if you can guarantee it completely.
The second question is, can you go back to this like a diagram with temperature from like 0 to yeah. So the regime where you said quantum advantage in a supremacist test sense. Can there be any macroscopic observable which can only be like okay, simplest example is a high TC.
Yeah.
Like can there be some meaningful observable which can have a non-trivial value in that regime, but not like classically simulable?
Yeah, I mean, I guess that's the hope, no? I mean, there's some material, no, for which we need a quantum computer to study it, no? So that's one. But yeah, I mean, I for sure I don't know the answer to this question. Yeah.
Hi, thank you for a nice talk. I actually have some questions. So first one is that about the Davis generator. You said that it is non-occur, and you said that it is a main problem. But in the view of some eigenstate summarizing hypothesis, of course, we don't know it is true. But yeah, in terms of that, I think Davis operator must be at least quasi-local in some sense.
With the ETH?
Yeah, with the ETH.
I wouldn't think so, no, because I mean, here in this, I mean, if we're talking about exactly these jump operators, I don't think the ETH helps you here. And in fact, the ETH exactly tells you that this thing is a mess, right?
Okay.
So I suspect that in ETH systems, these operators are very complicated. It might be that there's some approximation to this where you don't resolve the frequency completely, and then in that case, maybe ETH helps you in simplifying your Lindbladian.
Wow.
But this exactly no.
Okay.
But maybe approximately yes.
Yeah. The second question is that in the derivation of in the Bladian, I think it is did you actually take the account of the interaction of the boundary of system and the environment, or it is some type of what type of the Hamiltonian actually describing the system and environment the interactions?
The interactions, yeah. So we don't have to make. I mean, the assumptions. Okay, so the assumptions are, yeah. So we have this. Yeah. So we have these Hamiltonians, right? And the Hamiltonian in the interaction Hamiltonian has two operators, this one and this one. And what's important for instance, what is important of this is that the correlation functions of the bath kind of decay quickly. When you look at this.
But I also have some kind of suspicious about the A system because I mean, to describe the real summarization process, I expect that the A system must be also some type of boundary operator of the system, right?
Why? Boundary operator? How? I don't know.
I mean, it is basically the interaction. I mean, for example, like any matter, interact with the bath, only the atoms of the boundary of the matter interact with the environment, right?
So you're saying that okay, so this should be if you have a system that is large, like only the boundary should interact with the path. I mean, like that you can take that into account here by just saying that these have support on the boundary. This is just a matter of how you define this.
So the reason why I asked this question is that I expect that we should be able to derive some type of macroscopic heat equation from the Lindbladian if our Lindbladian is really correct. Yes. However, it's not really obvious from this point of view.
Heat equation. I mean, I will hope that something like this, the detail balance is an important step in proving that, right? The detail balance of the master equation. So hopefully that helps. But maybe that's not enough. I don't know.
Okay, very nice talk. Could you back to your Feynman gateway history state?
Yep. Somewhere here, maybe.
Oh, here. Okay, here. Look at this. You have the unitary U1 up to UT. This is what is it? Stochastic or something else? So what is your process on this unitary process?
What is this? So this is what this is essentially a mapping between circuits and Hamiltonians.
Right.
So I take a circuit, any circuit you want with polynomially many gates, and with this circuit, since I know what the gates are, I can define a Hamiltonian for which the ground state looks like this.
Right.
And these are going to be the gates of my circuit.
Okay. And then which Hamiltonian get on history
This is the history state Hamiltonian.
No, both of them, your clock and socket, both of them you can get.
Both of them are So this entire state is the ground state of this.
Okay. And then how about including environment? What happens? You are the processor.
So Well, I guess that you can answer in many ways, no? How, if you include environment in the, for instance, in your computation, or what kind of
You
environment?
look at this 1980s, the heart hacking wave function. This, I think that this also history dependent wave functions.
Right, because there you also have some sort of clock, right?
That's right.
Yeah. So I guess the idea is probably similar, but I don't know exactly.
That's right. Similar to this.
Yeah. Yeah, I guess if you forget about
In the 90s, I think that in the 90s, the German and the heart to work on this kind of history is kind of the same.
Okay, is this?
I think similar things, but it's quite different. You include the software.
Yeah, but these Hamiltonians are designed with quantum computation in mind, right? So this is, yeah.
So you mentioned this result on the continuity of rapid mixing. So how general is that? For example, if I had an invariant which wasn't like genuinely rapidly mixing, but it was rapidly mixing from some particular initial conditions, does it still work?
Oh, right. I think it. I don't think it will directly, but maybe you can make it work. I'm not sure. I mean, for sure, at some point we take some Hölder inequality. That means we forget about the initial condition. That's a good question. I would like to think the answer is yes, but I don't know actually. Yeah. I mean, for sure, this type of high level proof that we use is, I think you can make it more general, right? So you can kind of abstract it away and make it more general. So I don't see why. Yeah, something to look at for sure.
Okay, maybe last question. So your Fourier transformation is Gaussian envelope only in the temporal direction. How does it get a spatially quasi-local profile?
Yeah, so well, because I mean, so the jump operators are, well, in the simplest case, the jump operators are these. So this is a time evolution modulated by this function.
Right.
So if this integral, you can somehow, you can truncate it with a finite time, and then the error you make is the how small this function is.
So this is like a quasi-local along time, right?
No, this doesn't depend on time, right?
You just decide A to be a local operator.
Yeah.
Okay.
This is like a single side Pauli or something like that.
Okay, I see.
Yeah, so you just do the Robinson basically.
Okay, so I think well, let's thank Alvaro for a
Thanks.
very nice talk. And